Welcome to this explainer. Okay, I want you to picture this. You're standing right on the bridge of a massive, deep-water drill ship, just looking out at the open ocean. Suddenly, an alarm completely shatters the silence.
Fire in the engine room. Now, look, on a standard cargo vessel, yeah, that's a serious crisis. But you've got options, right? You can shut down the engine, drop the anchor, or just let the ship drift while the crew fights the blaze. But on a drill ship? No way. Drifting is absolutely not an option. That is a totally different story with unimaginable consequences.
So, let's really dive into this. How on earth do you keep a 77,000-ton drill ship perfectly still over a live subsea well when an engine room is literally burning? To put that immense weight into perspective, the crew actually deliberately floods the hull with 11,500 metric tons of ballast water just to push the ship down to its 11-meter operating draft. It buys them a calmer ride, sure, but it also means you're trying to hold an astonishing amount of mass perfectly stationary. You're fighting ocean currents, wind, and waves, all while part of your ship is on fire. This isn't just a minor inconvenience, folks. It is the ultimate engineering test.
To truly grasp the catastrophic stakes at play here, we have to look at what's hanging from the bottom of this 77,000-ton behemoth. We're talking 10,000 feet of rigid marine riser pipe. Think of it like a massive, incredibly heavy straw directly connecting the vessel to a wellhead on the seafloor. And that wellhead? It could be pushing back with 15,000 pounds per square inch of pressure. If the ship loses its station-keeping ability and just begins an uncontrolled drift, that rigid riser is going to bend and snap. Best case, it leads to an emergency riser disconnect. Worst case, a severe well control event where highly pressurized hydrocarbons are unleashed into the ocean. Because of this, holding position is an absolute non-negotiable requirement.
So how do we guarantee the ship stays put? Well, it really comes down to the critical difference between standard redundancy and true survivability. In DP2 or DP2, you definitely have backup equipment. But the fatal flaw? A single fire or flood in a shared space can wipe out both the primary system and the backup, causing a total loss of position. And sadly, that has happened in the real world. DP3, however, demands physical separation. The backups are entirely physically isolated. It guarantees that a disaster in a single space absolutely cannot cascade and take down the entire ship's capability.
And that brings us to the ultimate rulebook for deepwater survival, ABS DP3. This is the absolute highest dynamic positioning class notation available. It certifies that absolutely no single fault, even a worst-case fire or a massive flood in any one compartment can cause a loss of position. This isn't just a set of polite guidelines or best practices. It's a strict mandate required by regulators and operators before a ship is even allowed to operate over a live deepwater well.
The progression of safety across the different dynamic positioning classes is actually pretty straightforward once you break it down. DP Class 1, no redundancy is required at all. DP Class 2 requires redundancy, but as we just saw, it's still highly vulnerable to a single-space fire, wiping out those shared systems. But DP Class 3 completely changes the game. It mandates both redundancy and strict physical and electrical separation. It is literally the only class where you mathematically and physically cannot lose your position from a single localized event.
Now let's clear up a massive misconception. A lot of people think DP3 just means slapping a bunch of extra backup thrusters onto the hull of the vessel. It really doesn't. A ship like the GF12000 already has 6 massive 5.5 megawatt thrusters for its normal capability. DP3 isn't about raw quantity, it's about guaranteed isolation. It's all about making absolutely sure that a disaster in Room A can never ever reach the redundant equipment running over in Room B.
So what does this isolation actually look like inside the massive steel skeleton of the ship? Well, you have an immense power plant. We're talking enough electricity to power a small town, split into 3 completely separate engine rooms. These rooms are divided by longitudinal A60 fire-rated watertight bulkheads, meaning they can literally withstand a direct fire test for 60 minutes. The 6 thrusters are divided among these isolated power grids, and the DP control computers are entirely network segregated. If a catastrophic fire destroys an entire engine room, you only lose 1/3 of your total capability. The remaining 2/3? They stay completely safe, online, and keep the ship securely locked on station.
And you know, the technology making this control possible has evolved incredibly over the years. Back when dynamic positioning first started out, legacy DP control systems were these massive mainframe computers, literally the size of an entire house. But thanks to modern miniaturization, the industry standards today, like the Kongsberg DP3 systems, are modest desk-sized units. Because they're so beautifully compact, you can have 2 complete, fully redundant, and physically separated control systems sitting comfortably right on the bridge without sharing a single physical vulnerability. To really wrap your head around this,
Think of DP3 like a twin-engine aircraft losing one engine mid-flight. The plane doesn't just fall out of the sky, right? It keeps flying safely. That's because the aircraft's systems were deliberately designed and physically separated so that the sudden failure of one single component never cascades into a total failure. DP3 applies that exact, life-saving logic to a floating drilling platform holding millions of pounds of steel.
Okay, so we have all this brilliant engineering perfectly mapped out on paper. We've got the A60 bulkheads, the isolated networks, the segmented power grids. But how do we actually know it works before disaster strikes? Because you definitely cannot wait for a real engine room fire to find out if your ship is going to drift off a live well and cause a massive environmental catastrophe.
The answer is FMEA, which stands for Failure Mode and Effect Analysis. Before a drill ship ever accepts a contract, and definitely before it ever spuds a well, it has to undergo this grueling, systematic engineering study. Engineers literally traced every single credible failure point through the entire system. They do this to practically and mathematically confirm that the vessel retains sufficient thrust and control to hold its ground, no matter what happens.
Let's quickly walk through how this FMEA proving process works in practice. First, they identify a catastrophic failure. Let's say completely flooding the center engine room. Then they trace the effect. What cables, cooling systems, and thruster power grids go completely dark because of that flood? Next, they verify the remaining capability. Do the surviving engine rooms still provide enough power to the thrusters to fight the ocean current? Finally, it's a simple pass or fail. During sea trials, they literally simulate breaking the ship on purpose just to mathematically prove its DP3 rating is the real deal.
But, and this is a massive, absolutely crucial warning that every engineer and watchkeeper has to respect, we really need to be clear about the limitations here. DP3 is single failure tolerant. It is emphatically not failure proof. The entire ship is designed to survive the very first worst-case failure. But if a second, completely unrelated failure occurs while the vessel is already in that degraded state, it can still cause a total loss of position. That's exactly why watchkeepers must never ever treat any active fault as a low priority. Plus, the system runs continuous what-if simulations in the background. If the alert light flashes yellow on the console, it doesn't necessarily mean something just broke. It means your safety margin against a hypothetical single failure has shrunk, maybe just due to an uneven power load.
Which leaves us with this final thought for today's explainer. If you're the operator sitting at that console and that alert light flashes yellow while you are connected to a live well thousands of feet below, are you treating it as a minor glitch or as the dangerous end of your single failure safety margin? It's a high-stakes question that demands absolute vigilance. And honestly, it really makes you wonder, how does the dynamic positioning system even sense its exact position in the water in the first place to know if it's drifting? Well, we'll have to explore those incredible redundant reference sensors in another explainer. Thanks so much for joining me. Keep learning, and I'll catch you next time.